A microoperation is an elementary operation performed on data stored in registers or in memory. The microoperations most often encountered in digital systems are of four types. Transfer microoperations transfer binary data from one register to another. Arithmetic microoperations perform arithmetic operations on the data in registers. Logic microoperations perform bit manipulation on data in the registers, and shift microoperations shift data within the registers. A given microoperation may be of more than one type. For example, a ones complement operation is both an arithmetic microoperation and a logic microoperation. We covered transfer operations last time, so let's take a look at the other three types. Here we see the arithmetic microoperations of add, subtract, increment, decrement, and complement. Subtraction is most often implemented through complementation and addition. Note that multiplication and division are not shown here because they're assumed to be implemented by sequences of basic microoperations. It is sometimes possible to implement multiplication directly. Now let's take a look at logic microoperations. Logic microoperations are useful in manipulating the bits stored in the register. These operations consider each bit in the register separately and treat it as a binary variable. Here we see the four basic logic microoperations. The not microoperation, represented by the bar over the source register name, complements all bits and is the same as one's complement. The AND microoperation can be used for clearing one or more bits in the register to 0. The Boolean equations x and 0 is equal to 0 and x and 1 is equal to x play a role in this. When we AND a binary variable with 0, this produces a 0, which clears things out. When we AND it with 1, the variable remains unchanged. The AND operation can also be used to selectively clear bits of a register in an operation called masking. The OR microoperation is used to set one or more bits in a register. The Boolean equations x OR 1 is equal to 1 and x OR 0 is equal to x tell us that when a variable is ORed with 1, it produces a 1. When it's ORed with a 0, it remains unchanged. We can also use this as a masking operation to cover up certain bits we don't want to consider. Finally, the exclusive OR microoperation can be used to complement one or more bits in a register. X OR 1 is equal to x naught, and x OR 0 is equal to x. When a variable is x ORed with 1, we get the complement, and we can use this to derive 1's complement. We can also use this technique in masking. Shift microoperations are used for lateral movement of data. The contents of a source register can be shifted either right or left. The left shift is towards the most significant bit, and a right shift is towards the least significant bit. Shift microoperations are used in serial transfer of data. They are also used for manipulating the contents of registers in arithmetic, logic, and control operations. The destination register for a shift microoperation may be the same or different from the source register. For a left shift microoperation, we call the rightmost bit of the destination register the incoming bit. For a right shift microoperation, we define the leftmost bit of the destination register as the incoming bit. The incoming bit may have different values depending upon the type of shift microoperation. Here we're assuming the incoming bit is 0 and the outgoing bit value is simply discarded. Of course, other assumptions and operations are possible. We can have single or multiple registers as the destination of all primary results. A single register may also serve as the source of an operand for binary and unary operations. Due to the close ties between a single set of storage elements and the microoperations, the combinational logic implementing the microoperations is assumed to be part of the register, and is called the dedicated logic of the register. For a single register, we can use the simple technique that uses multiplexers for selection. This will allow multiple microoperations on a single register. When we have logic which is shared by multiple destination registers, the combinational logic implementing the microoperations is called shared logic for the set of destination registers. Thanks so much for watching. This completes our exploration of the Mano, Kahn, and Martin textbook and covers the recommended material in the curriculum standards for digital logic. Thanks for